those things because logarithms are inverses of powers, but they are like the most perfect inverse that we will ever see. I mean, they really are. And when we graph them today, it really becomes obvious how the inverse is just so. Here's the thing. Let's say we have this. Right here. So you look at this and you say, oh, well, this is a logarithm and the base is 5. And this is an unknown power and the base is 5. So they undo each other. But it's not like undoing addition by having to subtract or undoing multiplying by having to divide. They just disappear. That says X. Logarithms are like magic. It's just gone. It's as perfect of an inverse as you could possibly get. So it really reverses the roles when we think about what's going on with this. So to start with, oops, that's kind of covered up for you. That's not good. There we go. A logarithmic function is the inverse of an exponential function. That's what it's for. It's the way that we undo it. And at one point I knew what, there's like a breakdown, logos, and then a rhythm at the end, but it has to do with the fact that logarithm just means undo. Undo. Just undo in the Greek language. So the graph here shows y equals 10 to the x and its inverse, which is a logarithm. And yeah, I know we're not supposed to put the base there, but it makes more sense. If you look at that and you say, okay, if you want to undo a base of 10, you're going to have to use a logarithm base 10, and that's our common logarithm. And we can see, if we reflected this over the line, y equals x, we'd go from red to blue, equal but opposite on the other side. And like it says, totally turns things backwards. If you have the point 0, 1, which we had in the red, it becomes 1, 0. Well, that's not new. We've done that with inverses all along. That's not the new piece. But we'll see as we work through this how things are just so perfectly opposite. And it says 1, 0, and 10, 1 are on the graph of y equals the logarithm of x because 0, 1 was on this graph and 1, 10 was on this graph. So you just flip the x's and the lines. Recall that the graphs of inverse functions are reflections of each other across the line y equals x. You can graph y equals the logarithm base b of x as the inverse of y equals b to the x. And that's what we want to do today. That's part of our objective that is covered up there at 7.3 where it says write and evaluate logarithmic expressions and then graph logarithmic functions. And as long as we understand them, it goes super fast. It really does because they are such perfect inverses of those powers. So this says we're going to graph a logarithmic function. What is the graph of y equals logarithm base 3 of x? Describe the domain, range, identify the y-intercept, and the asymptote. It's brand new to us. So first thing I do, because I'm a right-handed snail shell person, is I just reverse that and make it logarithm base 3 of x equals y. Because here's the thing, we just learned about logarithms, and it's kind of like learning Spanish, you know, or any language for that matter. When you first learn the language, they say a word, and you stop, and you think, okay, what does that mean in English? Oh, that's what it means. So there's like this little pause where you have to think, okay, that's what that means. We don't know enough about logarithms at this point to think in logarithms. So what we do is what we know how to do, which is snail shell it, so it makes sense. So we're going to start with our base, and we're going to make our little snail shell, and we'll have 3 to the y equals x. And this is what's so cool. We always say that inverses switch the x and the y, and then solve for y. Literally, with logarithms, the x's and the y's switch positions. We are not going to be finding x's to put into this function. We're actually going to be using the y's as our inputs. So we're still going to make a table. It's just that normally we would use x as our independent variable and put in whatever we want. But because these are such pure inverses, we get to put in y values. So I start to think about what would happen if I put negatives in there. And I see there's a fraction right away. So I'm not going to need a whole lot of those. So maybe I'll just use -1. because that fraction tells me I'm approaching an asymptote. And then 0, 1, and 2, and that's probably going to be enough for our graph. Now, these are the values that we raise 3 to this power. So 3 to the negative 1 would be flipping it. It's going to make it 1/3. 3 to the 0 is 1. 3 to the first is 3. And 3 squared is 9. But now here's the risk. Every once in a while people get thinking backwards on this and they graph backwards. We don't graph backwards. All we do is make our table backwards. So we're still going to graph 1/3 to the right and 1 down. So just don't get turned around on this. 1, 0, 3, 1, and 9, 2. And again, if you needed to, you could put a negative 2 in there, but you realize that's going to flip it and it's going to square it. So if we had 1/3 times 1/3 or 1/3 squared, that would be 1/9. So it's getting closer and closer and closer, but it's never going to touch the y-axis. Wait a minute. When we did powers before, wasn't our asymptote always the x-axis? That's how pure and inverse this is. It even took the asymptote and said, hey, if we were using an asymptote of the x-axis before, now the asymptote is the y-axis. We're never going to quite get there. So even that has switched position. Totally inverse of what we had. So our domain, well, we're not going to get every x on the planet anymore like we did with powers, because our x's have been cut off right here. And the y-axis, remember, has the equation x equals 0. We're never quite going to get there, and we're always going to be on the right. So x is greater than 0. I'll just label my asymptote right there. Y-intercept. Well, if the y-axis is our asymptote, can there be a y-intercept? No, bless you. Okay. Range? Well, we were picking the y's, and we could put whatever y's we wanted into this thing. So the range now is all reals. It used to be the domain was all reals when we were working with our powers, with our exponents. And now we get a vertical asymptote. And again, if there's no h or k shift, that's going to be x equals 0, the y-axis. If there's an h or k shift, well, then we have to talk about which one of those is going to move that asymptote. So here's what I want you to think about for a second. Is it going to be h, our right and left movement, or k, our up and down movement that will affect the asymptote of y over x? And then chicken wing it out the partner and tell them what you think. Anybody have an idea and a way to explain it?
Nope.
Okay, kind of a stumper because spring break was kind of long, right? All right, so here's what we're saying. If we move this graph, and don't put this in your notes, but if I take this graph and I move it here, is my asymptote changed? Or if I take this graph and move it here, does the asymptote change? Which one of those makes that happen? The one to the left or the one that's down? The one to the left. So when we were dealing with exponents, it was always the k value, the up and down, that gave us a new asymptote. Logarithms, perfectly inverted. So we're looking at what does h do in order to give us that new asymptote as we go through it. So this one says, basically, let's do the same thing with y equals logarithm base 4 of x. So I think it's time we had pictures.
Yes.
Okay, so give this one a try. Set her up, do your snail shelling, make your table. Hopefully by that point I'll have a piece of candy on your desk for you. Oh, just, did you need one too? Just take down one, I got plenty of spares. All right, it looked like a lot of people were already to the graphing part on this one. So let's stop and just make sure we're getting the right numbers with each other. Candy up in the air. And Joey's going to use the Twix for his partner. Yeah, should be twos for everything else because we are missing two today. So should be a partner for everybody. So looking a lot like our other graph. This one, it's almost flat. I mean, we're going out to 16 too. It's not, but almost is flat. So you just kind of want to aim at where that 16.2 would be out there. So what's your domain?
X is greater than 0.
Mm-hmm.
Yeah.
Didn't have an H to move anything there. X is greater than 0. Y-intercept?
None.
Don't get one.
Yeah.
Always an important feature when we were talking about our exponential graphs, but with this one we don't get one. Range?
All real.
Put in whatever you want for Y's. Vertical asymptote was? X equals 0, exactly. We always want to have an equation for that line. Absolutely. So there it is. Yeah, rock stars. I mean, I'm walking around, everybody's got all the right answers before we even got together here. So now, what could make it more difficult? Well, a little bit more difficult would be the H and K. You know, what happens when we do have an H and K? That's really the only thing that can make it more difficult. But in the past, you guys have done great with H and K, so I really don't see this as being some kind of struggle. So if we had y equals the logarithm base b of x, that's the parent function. And so that we can understand it, we would just snail shell it, we would graph it, and realize that the x's and y's are actually changing roles. Independent becomes dependent, and dependent becomes independent when you do that. So we can graph, and we do graph, y equals logarithm base b of the quantity x minus h plus k. The only thing that some people struggle with about this one is, how do you know if it's h or k? There have to be parentheses for h. The grouping symbols have to say, this is affecting the x in order for that to be an h. So it's pretty basic stuff. By translating the graph of the parent function y equals logarithm base b of x horizontally by h units and vertically by k units, and then of course we might have an a in front of there to tell us whether or not that's going to be a vertical stretch or a compression. Now, what that does is messes things up a little bit. And so that's one I'm probably not going to have you do with your partner, but we'll do a couple of these just to make sure that we get the H and K piece right first. So that A in front, stretch compression, it's negative, could see a reflection in there as well. So if A is a number bigger than 1, vertical stretch, fraction between 0 and 1, going to be compression, negative, going to flip that thing over the x-axis. So here's a box that just puts it all together for us, and it is no different than any other box that we've had talking about the families of functions before. You know, it just goes through. Here's your stretches, here's your compressions. If you see a negative in front, you've got a reflection. Translate h units, but this time we know this is where our asymptote is going to come from. Because that shifting right and left is what gives us a new vertical asymptote. And of course down here, all of them together. Well, you have an E in front. What's that doing? What's the H So now we want to see how awful, I guess, is it to make the H and K switches? Well, it isn't awful. I mean, it's what we just did, and then we count and we move it. That's all we do. So when we see how does the graph of y equals logarithm base 4 of x minus 3 in parentheses plus 4 compared to the graph of the parent function, when we graph this, all we're going to do is take y equals logarithm base 2 of x. Now we need to take a with it, but a is just 1 in this one. So we'd start by just saying, all right, that's how I begin. Because what I know is that all I have to do is move this when I'm done. Those H and K units. So to answer their question, how does it compare, all we have to do is tell them how to translate this. So if it's x minus 3, where's the graph going to go? 3 to the right. And if there's a plus 4 in back, where's it going? Up 4. So translate 3 right and 4 up. But that's the last thing we do. The first thing we do is just get the shape. And the shape comes from our little graph of the snail shell. So 4 to the y equals x. And it turns out we just did this one. It's not like the difficult thing anyway, but kind of nice that we can just reuse that one. So this one now needs to be dashed or dotted. This is not our final. So you got ahead of me, huh? There we go. And then all we have to do is count to get it to the new one. But one of the things that I will always do before I move it anywhere is put on my new asymptote, because I don't want to accidentally cross it. That's a big no-no. So I'm going to look at this and say, well, if it's going to go 3 to the right, I had x equals 0 as my asymptote, and now it's going to be x equals 3. So I'm going to put that asymptote on here to make sure that I don't mess up.
Oh, I forgot to do it. I just did the same thing.
Upper lines. And then we just count. There it is. I think our domain has changed because we've got a new location for our assets. What should our domain be now? Good, Caitlin's got it. X is greater than 3. If our new asymptote is x equals h, because we are always going to use bases that are positive numbers, it's always going to be greater than. It's always going to go off to the right. Range? All reals. This is going down forever, and yeah, granted, it's not going up very fast, going from 4.1 to 16.2, but it's still going up. So all reals. So very close connection to just a basic snail shell graph by using that H and K. So down here we have how does the graph of each function compare to the graph of the parent function. So first thing you're going to do with your partner is describe what's the translation that's taking place here. And then I want you to go ahead and go through the graphing and the domain and range, but please don't do B. B has a numerical. So go ahead and
Forgot to do the dotted line again. Shit.
the risk at this point in the year is always that we've done this so often that, you know, it's the little steps that we kind of miss, the little details. We're so good at H and K. Make sure you talk to your partner about that domain and range.
What? That episode of Kid.
The domain and range was the exact same as the example that we did together before this. Explain to your partner why the domain and range is exactly the same as the graph that we just did before this. Yeah, heard everybody saying H and K were the same. H and K were the same. It's one of those things where in the past I thought, "Yeah, this is really silly that the book does this, you know? Maybe I should change this one and put some different numbers in there." But it really is important to see that it's H and K that are affecting that domain and range. You know, if we're always using a positive base for our logarithms, we're always starting off with the parent function having the y-axis as its vertical asymptote. So it's going to be that H and K, the H that affects our domain and our vertical asymptote, and then the K as that up and down shift. And then we get to B. They just had to throw an A in there. Well, yeah. And I look at this and I think, okay, if I'm supposed to compare this to the parent function, I know that's a vertical stretch. It's a vertical stretch factor of 5. Earth, are you supposed to deal with that when you're trying to make the parent function? Because again, this is the parent function right here. We see an A and we see the logarithm. There's no H and there's no K. So that's supposed to be the one thing that we graph. So I think, okay, math is logical. I'm supposed to do what I already know. So let me just ignore the 5 for a second. And if it weren't there, it would just be 2 to the y equals x again, because I would just snail shell it, and I'd get the exact same chart that I just used for this one. Okay, but the 5 is there. So now I'm going to go to the old standard, order of operations. If I were putting a number into this and actually doing the math, what would have to be done first and second, etc.? Well, I'd have to figure out what the logarithm base 2 of whatever this is first, because logarithms are powers, so they have to be done before multiplication. And once I have that answer, then I'd have to multiply my answer by 5. And that would give me y. Well, this was the power business. This is the logarithm. So all I have left is to multiply what I got for an answer times 5. Now, if you're saying, okay, but see, Erwin, that really wasn't our answer, we put those numbers in. But in this process of the order of operations, it would be the answer. You know, we were just using it backwards because it was an inverse. So my y's all get multiplied by 5. Now, don't accidentally graph the middle ones. Remember, that was the first step. And then we had to take a second step to get to our final answer. So it'll be 1/2 negative 5, 1, 0, 2, 5, and 4, 10. Pretty obvious vertical stretch, right? Huge. And that is my final graph. That's solid. There is no H and K on this one. If there were, it wouldn't be a big deal. I'd make this one dashed or dotted, and then I'd just move it, H and K units. What's the domain of this thing? X is greater than 0. Yeah, we didn't have an H. How about the range? Definitely could see it going down forever and up forever, right? On this one with this huge vertical stretch. Yeah, we definitely can see that piece. So it's just the A that's a little awkward with logarithms, But everything else is just a perfect inverse of what we know from before. So, 43210, Mick, how you feeling about graphing our logarithms here? Yeah, but yes, and everybody was perfectly fine until we had this A one here. Yeah. All right. Thank your partner for
Thank
the
you, partner.
wonderful help.
Thank you.
And of course, we'll be doing some graphing, so maybe while you're up, you might want to grab some graph paper.
Yeah, you want one? Yeah.
Joey's not M&M wrapper.
I do try. I really do.
All right. So it turns out, talking to my cohorts that teach Algebra 2, we are going to be testing on the whole chapter 7. So what I want to let you know is this. What we'll do is we'll go through the rest of chapter 7. Then we're going to spend the day just reviewing 7.1 and 7.2. And then we'll take one test. It's one piece of paper, front and back, on just 7.1 and 7.2. And then we'll come back and we'll spend another couple of days reviewing, and then we'll take the second test on the 7.3 through 7.6 material. Put plenty of review in there so we don't forget. That worksheet, it looked like most of you made your way through